Hello, engineering math student. So, you are here because you need to finish the notes on exponential graphs, and specifically, we need to look at exponential decay. So, you're going to see a lot of similarities to what we already talked about with exponential growth. In fact, you'll notice right here that this equation is the same equation that we had on the front of our notes. The only difference is right here, this b value, so we call that the base, remember, is between 0 and 1. And that's what's going to make this decay over time, as you see in the graph. All right, so let's look at just a couple of facts about these. Again, we mentioned this already, but the base is this variable b. And again, for decay, that number has to be between 0 and 1. The a value, the number in front, is the y-intercept. So if that happened to be 2, this right here would cross the y-axis at 2. The domain, just like exponential growth, is all reals. And again, you can use that double barred R to represent that. The range is specific. So the range is going to be above 0 if this number right here, if this is positive, you have y is greater than 0 because you're going to be above, you're going to have this shape. But if a is negative, so if we have a negative value for a, what happens is our graph actually gets flipped upside down and looks like that. So just be aware that those are both exponential decay. Just if it's negative, it's going to flip over. All right? So some end behaviors for you. If you think of what's happening at the extremes, or if you go very far out on this graph, if you go very far to the left, what's going to happen is this is going to go up, 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 and it's going to be going towards positive infinity. As you go to the right, so that's what this means, as x goes to the right, your function is getting closer and closer to 0. All right, and we're not going to talk a ton about horizontal asymptotes right now, but just be aware that anytime your graph levels off, we call that an asymptote. And in this case specifically, that's a horizontal asymptote. All right, but that should all be pretty familiar to what we talked about with exponential growth, because it's very similar. All right, so let's look at some examples. Just so you can differentiate between the two, remember exponential growth has a base that is above 1, and then exponential decay has a base, or a b value, that is between 0 and 1. All right, so really we only care about the number that has the exponent on it. That's going to tell us if it's growth or decay. So if we look at example 1, we have 4 times 5/8 to the power of x. To determine whether or not this is growth or decay, just look at that base. All right, so if we look at it, 5/8 is between 0 and 1. So I just noticed that it's less than 1. So we have decay. All right, and if we look at 6/5, well, that's 1 1/5. It's definitely bigger or greater than 1. So this would be growth. All right, and lastly, what's your base here? 2/3, and that is less than 1, so we have another decay. All right, so that should be pretty straightforward. we're going to look at one graph, and then that should be all you really need to finish up your homework. So if we take a look here, our last example is about graphing exponential decay models. So we are just going to, like before, pick some x values. I'm going to use my fave 5 again. Oops, skipped -1. So here's my fave 5. I guess since we've got room, we can throw 3 on there as well. And let's start plugging in and see what happens. So if we plug 0, our -2 into this function is going to be our first value. So f of -2. And here's where you can just use a calculator to help you out with this. So if you plug this in exactly as we write it, you're going to be just fine. And if you plug that into a calculator, you're going to actually get a number that won't fit on our graph. This turns out to be 16, so that won't fit, but oh well. Okay, and then we're going to plug in -1. So if we plug -1 into our function, we get 4 times 1/2 to the power of -1. That'll give us 8, which will fit on our graph. We can plug in 0. And if we do 4 times 1/2 to the power of 0, that's just 4 times 1, which is 4. And you can probably start to see a pattern here. We go to 16 to 8 to 4. Our base is 1/2, so these are actually going to cut in half over time. So once you see that pattern, we can just start doing that. You can also just keep plugging into the function like we're doing here, but we're going to cut that in half to get 2, cut the 2 in half to get 1, cut the 1 in half to get 0.5. And if we kept going, that would just keep happening where the values get cut in half. So now we can plot these points. The first one we will be able to fit is -1, 8. That's up there. And then we can do 0, 4, our y-intercept. Over 1 up 2, over 2 up 1, over 3 up 1/2. And then you draw this curve. And when you draw in your curve, be very careful that it's never going to cross the y-axis, so it levels off over time. All right, so there is our graph. We already talked about domain and range, but in this case, your domain is still all reals. Your range is this line where it's leveling off. So note that if you would shift this up or down, your range would change. But in this case, it's leveling off at 0, and it's above, so its y is greater than 0. And just a final note here before we finish up. Remember that decay models can still move with h and k, so these can be shifted. For example, I could have like a -2 here to shift it right, and then a +4 to shift it up. So these shifts right here can still happen. Just keep that in mind, that we can still shift these graphs just like what we did with exponential growth. All right, so that should be all you guys need to finish up your assignment. If you get stuck, I am here to help. All right, we'll see you guys later, or maybe right now if you're in class. Hello. All right, so that's it.